The light falling through a window right now has traveled 93 million miles to arrive at this exact angle, at this precise second, and it will never land quite this way again, not tomorrow, not in 1,000 years, not ever. There is something restful in knowing that the universe moves only forward, that each breath drawn is utterly singular, unrepeatable, a small event the cosmos will never attempt to recreate. The stars drift imperceptibly apart. The cells within a body replace themselves in quiet succession, and even the stillness of a room shifts in ways too subtle to name. If these kinds of unhurried reflections bring comfort on restless nights, perhaps this is a channel worth returning to. The moment that exists right now is already becoming the moment that came before, and so we follow that gentle current, letting the story unfold. In the ancient city of Ephesus, which stood along the western coast of what we now call Turkey, there lived a philosopher named Heraclitus, sometime around 500 years before the Common Era. He was known, even in his own time, as a difficult man to understand, someone who wrote in fragments and riddles, who seemed to delight in paradox the way others might delight in simple answers. But among the scattered pieces of his thought that have survived the long centuries, one observation has echoed across the ages with particular clarity, and it is this: you cannot step into the same river twice. The fragment, as it has come down to us, suggests that the river is always changing, that the waters which flow past your ankles in one moment have already moved on by the next, replaced by new waters from upstream, which themselves will soon be downstream and gone. And more than this, Heraclitus seemed to imply, you yourself are also changing, so that the person who stepped into the river the first time is not quite the same person who might step in again. The river flows. You flow. Everything flows. Panta rei, as the Greek has it. All things are in motion. And now, some 2,500 years later, you might find yourself lying quite still in a darkened room, your breathing slow and even, your body at rest, and you might feel, in this quietness, that you have found a moment of stillness, a pause in the great rushing of the world. The air around you is calm. The sounds have faded to a gentle hush. Your thoughts are beginning to soften at their edges, and the day that has passed feels very far away indeed. In this stillness, it might seem that nothing is happening at all, that you have found a pocket of time where the river has stopped flowing, where you might rest in the same moment for as long as you choose to rest there. But even here, even in this gentle pause, the ancient observation holds true. The air you are breathing is not the same air you breathed a moment ago. The oxygen molecules that entered your lungs with your last inhalation have already begun their quiet journey through your bloodstream, and they will be exchanged for carbon dioxide and released back into the room with your next exhalation. Your heart is beating, perhaps slowly if you are very relaxed, but still it beats, and each beat sends blood through vessels that branch and branch again into capillaries so fine that red blood cells must pass through them in single file in the darkness behind your closed eyes. Electrical signals are still flickering through the vast network of your neurons. And even if you are thinking of nothing in particular, even if your thoughts have gone quite vague and dreamy, the brain is still at work, consolidating memories, regulating the temperature of your body, preparing in its quiet way for sleep. You are, in every meaningful sense, still flowing. This observation, that things are always changing, that the present moment is always becoming the next moment, might seem rather philosophical, in the sense that it is interesting to contemplate, but perhaps not strictly scientific. And yet, as it turns out, modern physics has quite a lot to say about why the universe seems so deeply committed to this principle of constant change, and why exact repetition appears to be, if not strictly impossible, then so extraordinarily unlikely as to be functionally impossible, which amounts to much the same thing. The story of how science came to understand this begins, in many ways, with a German physicist named Rudolf Clausius, who was working in the middle of the 19th century on the theory of heat. Scientists at the time were very interested in steam engines, which were transforming the world around them, and they wanted to understand the fundamental laws governing how heat could be converted into work. In 1865, Clausius introduced a new concept to describe something he had noticed about these processes, and he gave it a name drawn from the Greek word for transformation. He called it entropy. The idea, at its heart, is that when energy moves or changes form, some of it becomes less available to do useful work. A hot object cooling down in a cold room is transferring heat to its surroundings, but once that heat is spread out evenly throughout the room, it cannot easily be gathered back up again to heat the object. The energy has not been destroyed, but it has become, in a sense, more dispersed, more spread out, more disordered. And Clausius observed that in any isolated system, entropy tends to increase, or at the very least stay the same. It never spontaneously decreases. This is the second law of thermodynamics, and while it might sound rather technical, it has profound implications for the nature of time itself. About a decade later, in Vienna, a physicist named Ludwig Boltzmann was working on what would become known as statistical mechanics, and he developed a deeper understanding of what entropy actually means. Boltzmann realized that you could think of entropy in terms of probability. Any physical system, whether it is a box of gas or a cup of tea or the entire universe, can be arranged in many different possible configurations, and some of these configurations are more probable than others, simply because there are more ways for them to occur. A shuffled deck of cards could, in principle, end up perfectly sorted by suit and rank, but there is only one such arrangement, whereas there are countless billions of arrangements that look shuffled and random. If you shuffle the deck fairly, you are almost certain to end up with one of those disordered arrangements, not because the ordered arrangement is forbidden, but simply because it is so vastly outnumbered. In the same way, Boltzmann argued, entropy increases because higher entropy states are just overwhelmingly more probable. A hot object cools down because there are enormously more ways for its energy to be spread out than for it to be concentrated. And so the spreading out happens naturally, inevitably, with a kind of quiet statistical certainty. This understanding of entropy helps to explain something that might otherwise seem rather mysterious, which is why time seems to have a direction at all. We remember the past, but not the future. Eggs break, but do not unbreak. Cream stirred into coffee mixes, but does not unmix. And while the fundamental laws of physics are, for the most part, symmetric with respect to time. The second law of thermodynamics gives time an arrow, pointing from lower entropy toward higher entropy, from order toward disorder, from the concentrated toward the dispersed. In 1927, the British astrophysicist Arthur Eddington gave this phenomenon a name. He called it the arrow of time, and he noted that it is deeply connected to the statistical behavior of large numbers of particles, to the overwhelming probability of moving toward more probable states. The arrow of time is not built into the fundamental equations of physics in the way that space and energy are, but it emerges nonetheless, as a consequence of entropy, as a feature of a universe that began in a remarkably low entropy state and has been unwinding ever since. And so, when you lie still in your darkened room, breathing slowly, feeling as though time has paused, the arrow is still flying. Entropy is still increasing. The molecules of your body are still jostling and rearranging themselves, and each new arrangement is different from the one before, if only slightly. The warmth of your skin is radiating into the cooler air around you, and this process is irreversible in any practical sense. The sound waves that carry the quiet hum of the room to your ears have dissipated into thermal energy that cannot be gathered back up. Every moment is a one-way journey, and even if you could somehow freeze all motion, you would find that the quantum uncertainties at the heart of matter would still introduce infinitesimal fluctuations, tiny changes that cannot be prevented. Consider, for a moment, the remarkable fact that your body replaces roughly 330 billion cells every single day. This is not a metaphor or an approximation, but a genuine estimate of the ceaseless activity happening within you at all times. Skin cells are sloughed off and replaced. The cells lining your intestines, which endure considerable wear, are renewed every few days. Red blood cells live for about 4 months before being recycled. Even the cells that last longer, like certain neurons and heart muscle cells, are constantly rebuilding their internal structures, replacing proteins, repairing damage, refreshing themselves at the molecular level. You are, in a very real sense, not the same collection of atoms you were a year ago, or even a day ago. The pattern persists. The unus continues. But the material is always being exchanged. You are a river flowing through matter, borrowing atoms for a time and returning them to the wider world. And the world itself is also moving, in ways that might be easy to forget when you are lying still. Since yesterday at this time, the Earth has completed nearly 1 full rotation on its axis, and you have been carried along with it, spinning through space at roughly 1,000 miles per hour, if you are near the equator, somewhat less if you are further north or south. But more than this, the Earth is also orbiting the Sun, traveling at about 67,000 miles per hour along its great elliptical path. And so, since yesterday, you have moved approximately 1.6 million miles through space, even though you felt as though you were staying perfectly still. And the Sun itself is moving, carrying the entire solar system with it as it orbits the center of the Milky Way galaxy. And the galaxy is moving too, drifting through the universe in ways that astronomers are still working to map and understand. The spot in space where you were lying yesterday no longer exists in any meaningful sense. The universe has expanded since then. The stars have shifted, and the cosmic microwave background radiation that fills all of space has cooled by an infinitesimally small amount, which it does continuously. The ancient afterglow of the Big Bang growing ever so slightly fainter with every passing moment. All of this might sound, at first, rather overwhelming, or perhaps even melancholy. This relentless change, this impossibility of holding on to any single moment. And it is true that Heraclitus himself was often described as gloomy, a philosopher who wept at the folly of those who did not understand the nature of flux. But there is another way to consider this, a gentler interpretation that might be more suitable for a quiet evening when you are preparing to rest. The fact that the universe is structurally incapable of exact repetition means that every moment, including this one, is in some sense unique. The particular arrangement of atoms in this room, in your body, in the air you are breathing, has never occurred before in the entire history of the cosmos, and it will never occur again. This is not a tragedy, but a kind of profound architecture, a feature of reality that gives each instant its own unrepeatable character. The evening light that fell across your window earlier today was not quite like any light that has ever fallen anywhere, because the sun was in a slightly different position, and the atmosphere had a slightly different composition, and the atoms in the glass were vibrating in their own particular way. The sounds of the day, the conversations you may have had, the thoughts that passed through your mind, all of these were singular, not because they were remarkable in any dramatic sense, but simply because they were themselves, occurring at their own point in the great unfolding. And so, as you lie here now, breathing slowly, letting your thoughts drift, you might take a quiet kind of comfort in knowing that you are participating in something genuinely unrepeatable. The universe does not repeat itself. Not exactly. Not ever. The river flows on. You flow with it. And tomorrow, when you wake, you will be a slightly different person in a slightly different world, carrying forward the pattern of yourself into a moment that has never existed before. This is not something to resist or to mourn, but simply to notice, gently, as you notice the feeling of the pillow beneath your head or the soft rhythm of your breathing. The cosmos is always becoming, always arriving at the next moment, and you are part of that becoming, part of that arrival, drifting now towards sleep in a universe that refuses to repeat. And that is, perhaps, what makes it so remarkable, in its quiet and ordinary way. For a time, it seemed as though the universe might be a kind of music box, one that would play its tune and then, given enough patience, play it again precisely as before, note for note, star for star, atom for atom. This was not a fanciful hope, but rather a reasonable conclusion drawn from the remarkable successes of a particular way of understanding the physical world, a framework built upon the careful observations and mathematical insights of natural philosophers who found, to their evident satisfaction, that the heavens moved according to fixed and knowable laws. In this section, we will spend some quiet time with this clockwork dream, tracing its elegant contours, admiring its considerable achievements, and then, without any particular urgency, watching it gently dissolve like morning frost under a patient sun. The story begins, as so many stories in physics do, with the motion of things through space, and in particular with the motion of those luminous wanderers that ancient peoples called planets, from the Greek word for wanderers, because they seemed to move against the fixed background of stars in patterns that were not immediately obvious. For centuries, astronomers had labored to describe these motions, piling circles upon circles in increasingly elaborate geometric constructions, until a German mathematician named Johannes Kepler, working in the early years of the 17th century, discovered something far simpler and far more profound. Between 1609 and 1619, Kepler published 3 laws that described planetary motion with unprecedented precision. And these laws had a quality that must have seemed almost miraculous at the time, for they suggested that the planets did not wander at all, but rather traced out the same elliptical paths around the Sun, over and over, with a regularity that could be calculated in advance. Kepler's first law told us that planets move in ellipses, with the Sun at one focus, and this was already a departure from the ancient preference for perfect circles. But it was a departure that brought the predictions into much closer agreement with careful observations. His second law described how a planet moves faster when it is closer to the Sun and slower when it is farther away, sweeping out equal areas in equal times, like a child on a swing who speeds up at the bottom and slows at the top. And his third law established a precise mathematical relationship between the size of a planet's orbit and the time it takes to complete one journey around the Sun, a relationship that held true for all the known planets and that seemed to hint at some deeper underlying principle waiting to be discovered. What Kepler had given the world was periodicity, the reliable return of celestial bodies to the same positions, following the same paths, at intervals that could be predicted years, decades, or even centuries in advance. The cosmos, it appeared, was not chaotic but orderly, not arbitrary but lawful. And if one knew the laws and had the patience to calculate, one could know the future as certainly as one knew the past. This vision of cosmic clockwork reached its fullest expression in the work of Isaac Newton, whose mathematical principles of natural philosophy, published in 1687, showed that Kepler's laws were not merely descriptions of planetary motion, but necessary consequences of a single, universal law of gravitation. Every object in the universe, Newton demonstrated, attracts every other object with a force that depends on their masses and the distance between them. And from this one principle, applied with sufficient mathematical skill, the entire dance of the heavens could be derived. The moon orbits the Earth. The Earth orbits the Sun. The moons of Jupiter orbit Jupiter, and all of these motions are manifestations of the same gravitational attraction that causes an apple to fall from a tree. The universe, in Newton's vision, was a vast machine operating according to immutable laws, and once set in motion, it would continue forever, its future entirely determined by its present state. Perhaps the most striking confirmation of this clockwork universe came in 1758, when a comet appeared in the night sky exactly where and when the English astronomer Edmund Halley had predicted it would appear. Halley had noticed, some decades earlier, that the comets observed in 1531, 1607, and 1682 had remarkably similar orbits, and he concluded that these were not 3 different comets, but the same comet returning at intervals of approximately 76 years. He predicted that it would return again around 1758. And although Halley himself died in 1742, 16 years before his prediction could be tested, the comet did indeed return, a luminous visitor arriving on schedule from the depths of space. This was not merely an astronomical triumph, but a philosophical one, for it demonstrated that the future could be known, that the universe did indeed operate like a great clockwork mechanism, and that human beings, armed with Newton's laws and sufficient skill in calculation, could peer into times they would never live to see. It was in this atmosphere of confidence that the French mathematician Pierre-Simon Laplace proposed a thought experiment that captured, perhaps better than any other formulation, the deterministic vision of the Newtonian universe. In his 1814 work, A Philosophical Essay on Probabilities, Laplace asked us to imagine an intellect vast enough to know the position and momentum of every particle in the universe at a single moment, and powerful enough to submit all this data to analysis. For such an intellect, Laplace wrote, nothing would be uncertain, and the future, like the past, would be present before its eyes. This hypothetical being has come to be known as Laplace's demon, though Laplace himself did not use that term, and the demon represents the logical endpoint of the clockwork worldview, a universe in which everything that will ever happen is already implicit in the present arrangement of matter and motion, waiting only to be calculated. In such a universe, repetition would not merely be possible, but, in some sense, inevitable. For if the cosmos is finite and bounded, if there are only so many ways for particles to arrange themselves, then eventually, given enough time, the same arrangements must recur. This intuition was given rigorous mathematical form by the French mathematician Henri Poincaré in 1890, in what has come to be called the recurrence theorem. Poincaré proved that in any bounded mechanical system governed by Newtonian laws, a system that cannot expand forever and cannot lose energy to the outside, the system will eventually return arbitrarily close to any initial state. Not exactly to the same state, perhaps, but so close that no measurement could distinguish between the two. And if one waited long enough, this near return would happen again and again, an infinite number of times. This might seem, at first, to vindicate the clockwork dream entirely, to prove mathematically that the universe must repeat itself, that every moment you have ever experienced will come again, indistinguishable from the original. But the apparent comfort of Poincaré's theorem dissolves when one considers the timescales involved. Even for very simple systems, systems with only a handful of particles moving in constrained ways, the time required for a Poincaré recurrence can be staggeringly, almost inconceivably long. For a system as complex as a box of gas containing billions upon billions of molecules, the recurrence time can exceed not merely the current age of the universe, which is approximately 13.8 billion years, but numbers so large that writing them out would fill more pages than exist in all the libraries of Earth. We are speaking of times like 10 raised to the power of 10 raised to the power of 10, towers of exponents that climb beyond any meaningful human comprehension. In practical terms, then, Poincaré's recurrence theorem tells us that while repetition is mathematically possible, It is so vanishingly unlikely on any timescale relevant to human experience, or to the experience of stars and galaxies, that we may safely set it aside. The clockwork returns. Yes, but the clockwork takes so long to complete its cycle that the clock will have rusted to dust. The workshop will have crumbled. The very atoms of the clockmaker will have dispersed to the far corners of an expanded and cooling cosmos, long before the hands return to 12. But there is another, more fundamental reason why the clockwork dream could not hold, and this too was discovered by Poincaré in the very same period when he was proving his recurrence theorem. It happened that King Oscar II of Sweden, in 1887, offered a prize for anyone who could solve the three-body problem, which is to say, the problem of predicting the future motions of three objects interacting through gravity. Newton's laws could handle two bodies perfectly well. Two objects orbiting each other trace out elegant ellipses that repeat forever. But the addition of a third body introduced complications that had resisted all attempts at solution for 2 centuries. Poincaré took up the challenge, and in his work on this problem, submitted in 1889 and revised in 1890, he discovered something that would eventually help bring down the clockwork universe entirely. What Poincaré found was that even in this seemingly simple system, 3 objects pulling on each other according to Newton's perfectly deterministic laws. The future could be, in a practical sense, unknowable. Tiny differences in the initial positions or velocities of the objects, differences too small to measure, could lead to vastly different outcomes over time. The orbits did not settle into neat, repeating patterns, but instead became tangled and unpredictable, sensitive to the smallest perturbations. Poincaré had glimpsed what we now call chaos, the discovery that determinism does not imply predictability, that even a clockwork universe can generate behavior so complex that no finite being could ever calculate it. This was a subtle but profound shift. The equations of motion were still deterministic in the strict sense, meaning that the future was still uniquely fixed by the present. But the sensitivity of those equations to initial conditions meant that any uncertainty at all, no matter how small, would be amplified over time until the prediction became useless. Laplace's demon could still exist in principle, but only if it knew the initial conditions with literally infinite precision, down to the last decimal place of an infinite expansion, and no finite measurement could ever provide such knowledge. The demon, it turned out, was an impossible being, and the clockwork it was meant to read was not the simple, predictable mechanism it had appeared to be. Poincaré's discoveries did not immediately overthrow the Newtonian worldview. Indeed, the full implications of what he had found would not be worked out until the second half of the 20th century, when mathematicians and physicists like Edward Lorenz began to study chaotic systems in earnest, famously discovering that even a simple model of atmospheric convection could exhibit the same sensitive dependence on initial conditions that Poincaré had found in celestial mechanics. The butterfly effect, the notion that a butterfly flapping its wings in Brazil might eventually cause a tornado in Texas, is a poetic expression of this mathematical reality. And it applies not only to weather, but to countless physical systems that had once seemed tractable. And so the clockwork dream, that elegant vision of a universe winding through its gears in perfect, repeatable cycles, dissolved not with a dramatic collapse, but with a gradual recognition that the very simplicity that made it appealing was an illusion. The laws were still there, as precise and universal as Newton had believed. But the behavior those laws generated was far richer, far more tangled, and far less predictable than anyone had imagined. The comet still returns, because the solar system is stable enough over the timescales of human civilization. But the leaves falling from the trees in autumn, the patterns of frost on a window, the exact arrangement of stars in a galaxy a billion years hence, all of these are subject to a complexity that forever outpaces our ability to calculate. You may rest now in the knowledge that the universe did not betray its early promise of order. The order is still there, encoded in the laws of physics, but it is an order that generates endless novelty rather than endless repetition. The music box does not play the same tune twice, not because it lacks a mechanism, but because the mechanism is so intricate, so exquisitely sensitive, that each performance is unique, a variation that could never have been predicted. A melody heard once and then gone forever into the soft, encircling dark. And so we find ourselves arriving, quite naturally, at a realm of physics where the impossibility of repetition is not merely practical but fundamental, where the universe itself seems to generate freshness at its very foundations, in ways that cannot be predicted even in principle, even by a being of unlimited intelligence with perfect knowledge of all conditions. This is the domain of quantum mechanics, and it offers us something rather remarkable to contemplate as we settle deeper into the quiet of this hour, which is the discovery that randomness, true randomness, appears to be woven into the fabric of reality itself, threaded through every atom, every particle, every flickering transaction of energy that comprises the physical world, including the very body in which you rest, the very neurons firing softly as you listen to these words. The story begins, as so many stories in physics do, in the early decades of the 20th century, when a young German physicist named Werner Heisenberg was working at the University of Göttingen and thinking very deeply about what it means to measure something at the smallest scales of existence. In 1927, he published a paper in the German physics journal Zeitschrift für Physik. And in this paper, he articulated what has come to be known as the uncertainty principle, though the German word he used, unschärf, might be more accurately translated as blurriness or indeterminacy, a slight softening of edges rather than mere ignorance. What Heisenberg demonstrated, through careful mathematical reasoning, was that certain pairs of physical properties cannot both be known with arbitrary precision at the same time. And this limitation is not a failure of our instruments or our cleverness, but rather a fundamental feature of how nature operates at quantum scales. The most famous example concerns position and momentum, which is to say, where a particle is and how fast it is moving. Heisenberg showed that the more precisely you determine a particle's position, the less precisely you can know its momentum. And conversely, the more precisely you measure its momentum, the fuzzier its position becomes. This is not because your measurement disturbs the particle, though early interpretations sometimes described it that way, but rather because a particle simply does not possess both a definite position and a definite momentum simultaneously. The properties themselves are indeterminate until measurement, and even then, the act of measuring one necessarily leaves the other uncertain. It is as if the universe keeps certain combinations of knowledge permanently out of reach, not from spite or secrecy, but because definiteness in one domain requires indefiniteness in another, a kind of cosmic trade-off built into the mathematics of existence. While Heisenberg was developing these ideas in Göttingen, another profound thinker was working in Copenhagen, at the Institute for Theoretical Physics that bore his guidance. And this was Niels Bohr, the Danish physicist whose model of the atom had already transformed our understanding of matter. Bohr's institute became a gathering place for the brightest minds in quantum physics during the 1920s and 1930s, a place where young scientists came to discuss, debate, and gradually construct what would become known as the Copenhagen interpretation of quantum mechanics. This interpretation held that quantum systems do not possess definite properties until they are measured, that the wave function describing a quantum system represents not the system itself, but our knowledge of it, and that the act of observation plays an essential role in bringing physical outcomes into being. The discussions at Bohr's Institute were long and sometimes contentious, carried out in that slow, deliberate manner of scientists genuinely trying to understand something unprecedented, sitting in offices and walking along Copenhagen's grey waterways, turning ideas over like stones in a stream. Not everyone was comfortable with these conclusions, and among the most eloquent dissenters was Albert Einstein, whose contributions to quantum theory in its early years were themselves foundational, including his explanation of the photoelectric effect that first revealed light's particle-like nature. Einstein found himself deeply troubled by the randomness that seemed to lie at the heart of quantum mechanics. The suggestion that nature's outcomes were not determined by prior causes, but emerged from genuine chance. In 1926, a year before Heisenberg's uncertainty paper, Einstein wrote a letter to his friend and fellow physicist Max Born, and in this letter he expressed his famous objection that has echoed through the decades of physics since. He wrote that the theory accomplishes a great deal, but brings us no closer to the secrets of the old one, and that he, Einstein, was convinced that God does not play dice. It was not a statement of religious belief so much as a deep conviction that nature must ultimately be deterministic, that the apparent randomness of quantum mechanics must conceal some deeper layer of hidden variables, some mechanism we had not yet discovered that would restore causality and predictability to the foundations of physics. This disagreement between Einstein and Bohr became one of the great intellectual debates of 20th century science, and it came to a head most memorably at the Solvay conferences of 1927 and 1930. Those gatherings of elite physicists in Brussels where the future of quantum theory was shaped through formal lectures and informal discussions. At the 1927 conference, Einstein presented clever thought experiments designed to show that quantum mechanics must be incomplete, that there must be ways around the uncertainty principle, and each time Bohr would consider the argument overnight and return the next morning with a careful refutation, often using Einstein's own general relativity against him. At the 1930 conference, Einstein proposed what he thought was his most devastating challenge, involving a box of photons and a clock that seemed to allow simultaneous precise measurement of energy and time. And once again, Bohr found the flaw. showing that Einstein had forgotten to account for how the act of weighing the box would affect the clock's rate according to general relativistic time dilation. These debates were conducted with enormous mutual respect, for Einstein and Bohr admired each other greatly. But they never reached agreement, and Einstein went to his grave in 1955, still believing that quantum randomness must ultimately be explained by deeper deterministic laws. The question of whether quantum randomness is fundamental or whether it emerges from hidden variables that we cannot yet detect remained open for decades, seemingly more philosophical than empirical, until a physicist working at CERN in Geneva found a way to turn philosophy into experimentally testable predictions. In 1964, John Stuart Bell published a theorem that showed if hidden variables exist and obey certain reasonable assumptions about locality, meaning that influences cannot travel faster than light, then measurements on pairs of entangled particles must obey certain mathematical inequalities. If quantum mechanics is correct and randomness is fundamental, these inequalities would be violated. Bell's theorem transformed the Einstein-Bohr debate from metaphysical speculation into something that could actually be tested in a laboratory, though the experiments required to perform such tests were technically demanding and took nearly 2 decades to execute convincingly. The definitive experiments came in 1982, carried out by Alain Aspect and his colleagues at the Institut d'Optique in Paris, using pairs of photons entangled in their polarization states and measured at separate locations before any signal could travel between them at the speed of light. The results were clear and have been confirmed many times since with ever more rigorous controls. Bell's inequalities are violated, exactly as quantum mechanics predicts. This means that the randomness we observe in quantum measurements is not the result of our ignorance about hidden variables, not the consequence of some deeper deterministic layer we have yet to discover, but is instead a fundamental feature of reality itself. Einstein's conviction that God does not play dice, however emotionally compelling, appears to have been mistaken. The universe does play dice, or something very like it, generating genuinely random outcomes that were not determined by anything prior, not even in principle. This fundamental randomness manifests most clearly in phenomena like radioactive decay, which was first carefully studied by Ernest Rutherford and Frederick Soddy at McGill University in Montreal around 1902. Working with samples of thorium and radium, these pioneers discovered that radioactive substances transform into other elements at rates that are statistically predictable for large samples, but completely unpredictable for individual atoms. You can say with confidence that half of a sample of radium-226 will have decayed after 1600 years, but you cannot say, even with perfect knowledge of a single radium atom, when that particular atom will decay. It might happen in the next microsecond, or it might happen in 10,000 years, and there is no property of the atom, no hidden clock or internal timer, that determines the outcome. Each decay is a fresh event, a quantum dice roll with no memory of rolls that came before. And this randomness has been generating new, unrepeatable moments in every radioactive substance since the formation of the elements in ancient stars. There is another phenomenon worth mentioning as we rest here in the gentle consideration of these ideas. And that is the quantum Zeno effect, named after the ancient Greek philosopher whose paradoxes challenged our intuitions about motion and change. In 1977, physicists George Sudarshan and Baidyanath Misra published a theoretical analysis showing that the evolution of an unstable quantum system can be slowed or even halted by frequent observation, as if the act of repeatedly asking whether the system has changed prevents it from changing. This has since been confirmed experimentally and offers a strange window into the relationship between observation and quantum evolution. Yet even this effect does not eliminate randomness. It merely reshapes the statistical landscape within which random outcomes occur. The quantum dice are still rolling, just under different rules when someone is watching, and each measurement still produces genuinely new information that was not determined beforehand. What does it mean to say that every quantum measurement creates genuinely new, unrepeatable information? It means that when an electron passes through a detector and registers at a particular position, that outcome was not encoded anywhere in the universe before it happened. It means that when a photon passes through a polarizing filter and emerges with a particular orientation, that result is fresh, born in the moment of measurement, irreducible to prior conditions. It means that the universe is constantly generating novelty at its most fundamental level, adding to the sum total of what has happened in ways that cannot be predicted and cannot be repeated. Each quantum event is like a word spoken for the first time, a note that has never been played before, a decision that was made by no one and nothing but the bare mathematics of probability expressing itself in actuality. And here is the remarkable thing to hold gently in mind as you settle towards sleep. This quantum randomness is not confined to physics laboratories or philosophical discussions, but is woven into every atom of the world around you and within you. The carbon atoms in your muscles, the oxygen atoms in your blood, the calcium and phosphorus atoms in your bones, all carry quantum indeterminacy at their hearts. The neural signals traveling through your brain involve countless quantum events, each one generating outcomes that were not determined before they occurred. You are, in a very real physical sense, a walking expression of quantum randomness, a pattern made of countless dice rolls that have never landed quite this way before and will never land quite this way again. The cells replacing themselves in your tissues, the photons entering your eyes, the tiny electrical fluctuations in your nerves, all participate in this ongoing generation of newness. This continuous emergence of moments that have never existed in all the history of the cosmos. This is not cause for alarm or wonder or anything dramatic at all, but simply a quiet fact about the nature of existence, as reliable and as unremarkable as the turning of the earth or the ticking of a clock. The universe is not capable of exact repetition because it is built from components that do not repeat, because its smallest transactions involve genuine chance, because information is constantly being created rather than merely shuffled and recombined. The moment you are in right now, listening to these words in whatever room or bed you occupy, is unrepeatable not merely because of the practical impossibility of reconstructing every condition, but because the quantum foundation of reality does not permit exact copies. Each moment is the first of its kind, and there is something deeply restful in that, something that invites you to release any worry about repetition or monotony, and simply rest in the gentle flow of genuine, fundamental newness that carries you forward. The universe, it turns out, is not a closed room where events might eventually cycle back to their beginnings. Nor is it a static theatre where the same scenes could theoretically play out again given enough time. But rather, something far more quietly remarkable. A stage that grows ever larger with each passing moment, stretching outward in all directions, carrying everything within it further apart, and in doing so, ensuring that the precise arrangement of matter and energy that exists right now, in this very instant, as you settle into your pillow and let your breathing slow, will never, can never, occur again in quite the same way, because the cosmos itself is moving on, expanding into whatever lies beyond its current boundaries, though even that phrasing is not quite right, since it is not expanding into anything so much as it is creating more space as it goes. The fabric of reality itself growing roomier, more diffuse, more spread out, second by second, in a process that began billions of years ago and continues right now. Even as you listen to these words, even as the darkness outside your window holds steady and the night settles in around you like something soft and unhurried. This understanding of an expanding universe did not come to us all at once, but rather emerged gradually through the careful work of astronomers peering through telescopes at distant points of light, measuring wavelengths, taking photographs, and slowly, methodically assembling a picture that would have seemed quite strange to anyone living just a century or so ago. When the prevailing view held that the universe was essentially fixed, eternal, unchanging in its overall structure, a cosmos that had always been more or less as it appeared and would continue in that fashion indefinitely. A comforting notion in its way, though one that would eventually give way to something rather more interesting, if also more difficult to fully grasp. The idea that everything we see around us, every galaxy and cluster of galaxies, every far-flung nebula and distant quasar, is moving away from everything else. Not because of some explosion that flung matter outward through pre-existing space, but because space itself is stretching, growing, becoming more of itself, and carrying all the matter within it along for the ride. Among the first to notice hints of this cosmic stretching was an astronomer named Vesto Slipher, working at the Lowell Observatory in Arizona during the years between 1912 and 1917, a period when the nature of the faint fuzzy patches then called spiral nebulae was still very much in question, with some astronomers believing them to be relatively nearby clouds of gas within our own Milky Way, and others suspecting they might be far more distant, perhaps entire galaxies in their own right, island universes separated from our own by vast gulfs of empty space. And Slipher, using a spectrograph attached to the observatory's telescope, began carefully measuring the light from these nebulae, spreading it out into its component wavelengths and looking for the telltale lines that indicated the presence of particular elements. And what he found was curious indeed, for the spectral lines in most of these objects were shifted toward the red end of the spectrum, a phenomenon that indicated the light sources were moving away from Earth, receding into the distance at considerable velocities. And while Slipher did not fully understand the implications of what he was seeing, his meticulous measurements would prove essential to later discoveries, his data quietly waiting in observatory records for someone else to come along and fit it into a larger picture. That larger picture began to take shape in 1927, when a Belgian priest and astronomer named Georges Lemaitre working largely independently of the mainstream astronomical establishment, published a paper proposing that the universe was not static but expanding, that the galaxies were receding from one another, not because they were flying through space, but because space itself was growing larger, stretching out in all directions like the surface of a balloon being slowly inflated. And Lemaitre, who had studied both physics and theology, who had served as an artillery officer in the First World War and later earned his doctorate from the Massachusetts Institute of Technology, brought to the problem a particular combination of mathematical rigor and imaginative vision, deriving his conclusions from Einstein's equations of general relativity and arriving at what he called the hypothesis of the primeval atom. The idea that if the universe is expanding now, then it must have been smaller in the past. And if you traced that expansion backward far enough, you would arrive at a moment of extraordinary density. A beginning of sorts, though Lemaitre was careful to note that this was a question for physics rather than theology, that the scientific account of origins should be kept separate from questions of ultimate purpose or meaning. And his paper, published in an obscure Belgian journal and written in French, received relatively little attention at the time, his contribution often overlooked in the years that followed, though history would eventually recognize him as one of the true pioneers of modern cosmology. It was Edwin Hubble, working at the Mount Wilson Observatory in California with its powerful 100-inch telescope, who provided the observational evidence that would convince the broader scientific community. His 1929 paper demonstrating a clear relationship between the distance of galaxies and the speed at which they appeared to be receding, the more distant galaxies moving away faster than the nearer ones, a pattern now known as Hubble's law, though perhaps more fairly it should be called the Lemaitre-Hubble law. And this relationship, this simple proportionality between distance and velocity, was exactly what you would expect if space itself were expanding uniformly in all directions, each point moving away from every other point, not because there is some special center from which everything is fleeing, but because the fabric of space is stretching everywhere at once, like dots drawn on a rubber sheet being pulled outward, each dot seeing all the other dots receding, each perspective equally valid, no preferred location, no center, just expansion, everywhere, always, carrying everything along with it. And Hubble, building on Slipher's earlier redshift measurements and combining them with his own distance estimates based on the brightness of certain types of stars, assembled a picture that would fundamentally change our understanding of the cosmos, replacing the static eternal universe with something dynamic, evolving, changing with time. For decades after Hubble's discovery, the expanding universe remained something known primarily through the movement of galaxies, through the redshift of their light, through mathematical extrapolations backward in time. But in 1965, quite by accident, two radio astronomers at Bell Telephone Laboratories in New Jersey stumbled upon evidence of a rather different sort. A faint hiss of microwave radiation coming from all directions of the sky, a background noise that persisted no matter which way they pointed their antenna. And Arno Penzias and Robert Wilson, who had been trying to use the antenna for other purposes entirely, were initially perplexed by this persistent signal, checking and rechecking their equipment, even climbing inside the horn-shaped antenna to remove what they delicately referred to as a white dielectric material, but which was, in plainer terms, pigeon droppings, the accumulated waste of birds who had taken up residence in the antenna's warm interior. And yet, even after this thorough cleaning, the signal remained, coming from everywhere at once, uniform and unwavering. And it was only when they consulted with theorists at nearby Princeton University that they realized what they had found. The cosmic microwave background, the afterglow of the early universe, radiation that had been traveling through space for nearly 14 billion years, stretched by the expansion of the cosmos from its original high-energy form into the faint microwave hiss they were detecting. A direct observation of the ancient past. Light from a time when the universe was young and hot and dense, now cooled and diluted by billions of years of cosmic stretching. And this discovery, for which Penzias and Wilson would later receive the Nobel Prize, provided stunning confirmation that the universe had indeed begun in a hot, dense state and had been expanding and cooling ever since. The cosmic microwave background, as scientists would come to understand, is remarkably uniform, the same temperature in every direction to a precision of about 1 part in 100,000. A smoothness that speaks to the extreme conditions of the early universe, when everything was so close together and so thoroughly mixed that any irregularities were largely smoothed out. And yet, within that uniformity, there are tiny variations, slight differences in temperature from one patch of sky to another, fluctuations that would eventually grow, under the influence of gravity, into the galaxies and clusters of galaxies we see today. And measuring these tiny variations required extremely sensitive instruments, which is why, in 1989, NASA launched the Cosmic Background Explorer satellite, known as COBAO, designed specifically to map the microwave background with unprecedented precision. And in 1992, the COBE team, led by George Smoot, announced their findings, revealing for the first time the faint ripples in the background radiation, the seeds of cosmic structure, the slight density variations in the early universe that would eventually become everything we see around us. Every galaxy, every star, every planet, every person lying in bed, listening to a gentle narration about the nature of the cosmos. And Smoot, in a moment of perhaps forgivable enthusiasm, described the discovery as like seeing the face of God. Though in the context of our present discussion, we might simply say that it was like seeing the universe at a moment very close to its beginning, a snapshot of conditions that could never be recreated, a configuration of matter and energy that existed once and only once, frozen in the pattern of the cosmic microwave background. A fossil record of a cosmos that has been changing ever since. The expansion of the universe continues today, and thanks to observations made in the late 1990s, we now know that this expansion is not slowing down, as one might expect if gravity were gradually pulling everything back together, but actually speeding up, accelerating, driven by some mysterious influence that scientists have named dark energy, though the name is really just a placeholder for our ignorance, a label for something we can detect through its effects, but do not yet understand. And this accelerating expansion was discovered independently by 2 teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, who were measuring the brightness and redshift of a particular type of exploding star called a Type Ia supernova, which can serve as a kind of cosmic yardstick because these explosions always release roughly the same amount of light, allowing astronomers to calculate how far away they are by measuring how bright they appear. And what both teams found, to their considerable surprise, was that the most distant supernovae were fainter than expected, indicating that they were further away than a universe with a constant or decelerating expansion would suggest, meaning that the expansion of the cosmos must have been speeding up over time. The universe not just growing larger, but growing larger faster and faster. And this discovery, announced in 1998 and recognized with the Nobel Prize in Physics in 2011, added yet another layer to our understanding of cosmic change. The universe not only expanding, but doing so at an ever-increasing rate. Space stretching more rapidly with each passing moment, carrying the galaxies away from each other ever faster. The current rate of this expansion is measured at approximately 70 kilometers per second per megaparsec, which means that for every million parsecs of distance between 2 points in space, those points are moving apart at about 70 kilometers every second. And a megaparsec is a very long distance indeed, roughly 3.25 million light-years. So these speeds only become significant across truly cosmic scales. Not something you would notice in your daily life. Not something that affects the distance between you and your bedroom wall, or you and the nearest town, or even you and the moon. Since gravity and electromagnetic forces hold local structures together quite firmly, but across the vast empty gulfs between galaxy clusters, the stretching of space proceeds continuously, relentlessly, imperceptibly, adding more emptiness to the already enormous emptiness, ensuring that the overall configuration of the cosmos is always changing, always different from one moment to the next, each instant unique, not just because of the movements of particles and the flow of energy, but because the stage itself is growing, the container is expanding. The very space in which everything exists is becoming more of itself. And there is no mechanism, no force, no process that anyone has ever discovered or theorized that would reset this expansion, that would shrink the cosmos back to an earlier state, that would allow the universe to return to a configuration it once had. The expansion is a one-way process, a cosmic ratchet that clicks forward with each passing second, carrying everything with it, ensuring that the moment you are experiencing right now, nestled in your covers with the weight of the day slowly lifting from your thoughts, is truly singular, never to be repeated, not because repetition is merely unlikely, but because the universe itself will never again be arranged in quite this way. The distances between galaxies will never again be quite these distances. The age of the cosmos will never again be quite this age. And so, you may rest easy in the knowledge that this moment belongs to you, and to now, and to the particular configuration of an ever-expanding universe that will never quite exist again. The stars, those distant points of light that have watched over sleeping worlds for billions of years, are not merely decorative. They are factories, and they are furnaces, and they are, in the most fundamental sense, alchemists of the cosmos, though their alchemy follows strict physical laws rather than medieval dreams. What the stars do, moment by moment and eon by eon, is transform the universe in ways that cannot be undone, converting the simplest of atoms into more complex arrangements, burning through their fuel in a great slow fire that has been burning since the first stars ignited some 13 billion years ago. and which will continue burning until the last red dwarf finally gutters out in the incomprehensibly distant future. In 1939, a German-American physicist named Hans Bethe published a paper that would eventually earn him the Nobel Prize in Physics, though that recognition would not come until 1967, nearly 3 decades later. Bethe's paper described, with careful mathematical precision, the nuclear processes by which stars like our Sun generate their light and heat. He outlined what became known as the proton-proton chain reaction, a sequence of nuclear fusion events in which hydrogen nuclei, which are simply individual protons, combine under tremendous pressure and temperature to form helium nuclei, releasing energy in the process. This energy, this warmth that we feel on a summer afternoon, or that helps a seed germinate in spring soil, originates in nuclear transformations occurring some 93 million miles away, in the dense core of our local star. The numbers involved are difficult to hold in the mind, and perhaps that is fitting for a bedtime narration, since there is something almost hypnotic about contemplating figures so vast they slip past ordinary comprehension. The Sun, our star, converts approximately 600 million tons of hydrogen into helium every single second. 600 million tons, roughly the mass of a small mountain, transformed in the time it takes to draw a breath. And the Sun has been doing this for approximately 4.5 billion years, and will continue doing it for another 5 billion years or so, steadily and patiently converting its hydrogen reserves into helium, releasing photons that bounce and scatter through the solar interior for thousands of years before finally escaping from the surface and streaming out into space. Some small fraction of them eventually reaching our planet and our closed eyelids as we rest. But here is the gentle truth that underlies all of stellar physics, the truth that makes this process relevant to our meditation on the unrepeatable nature of time. The hydrogen that becomes helium does not become hydrogen again. The fusion reaction is not reversible, not under any natural conditions the universe provides. Once 4 hydrogen nuclei have been pressed together to form one helium nucleus, that helium nucleus will remain helium until something even more dramatic occurs. The star has, in a very real sense, burned a bridge, crossed a threshold that cannot be uncrossed, moved forward along a one-way chemical journey that the entire cosmos is taking together, slowly and inexorably, toward a future that will be different from the past, simply because matter itself will have changed its fundamental composition. Fred Hoyle, a British astronomer with a gift for vivid explanation and a sometimes controversial temperament, spent the years between 1946 and 1957 developing and refining our understanding of how stars manufacture elements heavier than hydrogen and helium. Hoyle recognized that the universe began with essentially only hydrogen, some helium, and traces of lithium, and that everything else, all the carbon and oxygen and nitrogen and iron and gold and uranium, had to come from somewhere. Stars, he argued, were the somewhere. Stars were the factories in which the raw materials of the early universe were processed, step by step, into the rich periodic table of elements we know today. In 1957, Hoyle collaborated with 3 other scientists, Margaret Burbidge, Geoffrey Burbidge, and William Fowler to publish a landmark paper that is still referred to simply by the initials of its authors, B²FHH, though it is sometimes written as B2FH in the manner of a chemical formula or a robot designation. This paper, titled Synthesis of the Elements in Stars, laid out in comprehensive detail the nuclear processes by which stars of various masses and ages create elements through fusion. A star like the Sun fuses hydrogen into helium, but larger stars, those with greater mass and higher core temperatures, can continue the process further. They can fuse helium into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, and so on up the periodic table, each stage requiring higher temperatures and pressures, each stage burning a little faster than the one before, until eventually the star reaches iron. Iron, element 26, is something of a dead end, a cul-de-sac in the stellar nucleosynthesis process. Fusing iron does not release energy. Instead, it requires energy to be put in. A star that has built up an iron core has reached the end of what fusion can accomplish. And if the star is massive enough, what follows is collapse and catastrophe. A supernova explosion of unimaginable violence that disperses the star's accumulated elements into the surrounding space, while simultaneously creating conditions extreme enough to forge elements heavier than iron, elements like cobalt and nickel and copper and zinc and silver and gold. In February of 1987, a supernova appeared in the Large Magellanic Cloud, a small satellite galaxy of our Milky Way, visible from the southern hemisphere as a faint smudge near the bright star Canopus. This supernova, designated 1987A, was the first supernova visible to the naked eye since the supernova observed by Johannes Kepler in 1604, a gap of nearly 4 centuries. Astronomers around the world turned their instruments towards this cosmic explosion, studying the light it produced, the neutrinos it released, the expanding shell of debris it created. Supernova 1987 A became one of the most studied events in the history of astronomy, and it provided direct confirmation of theories about how heavy elements are created in the death throes of massive stars. The light from that explosion, still traveling outward through the cosmos, carries information about nuclear transformations that cannot be reversed, about matter that has been permanently altered, about a moment in cosmic history that happened once and will never happen again in precisely the same way. But supernovae are not the only sites of heavy element creation. In August of 2017, the gravitational wave detectors known as LIGO, located in Louisiana and Washington State, and Virgo, located in Italy, detected a signal that was different from the black hole mergers they had observed before. This signal, designated GW-178-817, came from the collision and merger of 2 neutron stars, the incredibly dense remnants of stars that had already exploded as supernovae. When telescopes around the world turned toward the location of the gravitational wave signal, they observed something remarkable, a new point of light that faded over the following days from blue to red, a signature consistent with the theoretical predictions of what would happen when neutron-rich matter was flung out into space by such a merger. The observations of GW-178-817 provided the first direct evidence that neutron-star mergers are responsible for creating a significant portion of the heaviest elements in the universe. Elements like gold and platinum and uranium. In a sense, the astronomers of 2017 watched in real time, or as close to real time as the 130 million year travel time of light and gravitational waves allows, as matter was transformed in ways it had never been transformed before in that particular location. As new atoms came into existence that would persist for billions of years, as the universe took another small, irreversible step along its chemical journey. The American astronomer Carl Sagan, who possessed a remarkable ability to communicate the wonder of scientific discovery to general audiences, once reflected on the implications of stellar nucleosynthesis for our understanding of ourselves. The nitrogen in our DNA, he observed, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, were made in the interiors of collapsing stars. We are made of star stuff, he said. And this was not a metaphor or a poetic flourish, but a literal statement of physical fact. The atoms that comprise your body were once inside a star, possibly several stars, over the course of billions of years of cosmic processing. You are, in a very real sense, the universe experiencing itself, the cosmos having transformed enough of its simple hydrogen into complex chemistry that awareness has emerged from matter. And this transformation continues. Right now, as you lie still and breathe slowly and let your thoughts drift toward sleep. Stars throughout the observable universe are fusing hydrogen into helium. Massive stars are building up cores of carbon and oxygen and silicon and iron. Supernovae are exploding and scattering their processed elements into the interstellar medium. Neutron stars are spiraling toward collision, and the universe is becoming, atom by atom by atom, a different place than it was a moment ago. This process has been ongoing for more than 13 billion years, and it will continue for many billions more, though the pace will eventually slow as stars become less common, as the raw hydrogen fuel is steadily consumed, as the cosmos drifts toward a future dominated by iron and other endpoint elements that cannot be easily transformed into anything else through fusion. The universe, considered as a chemical system, is running down. It began in a state of relative simplicity, with vast clouds of hydrogen and helium and little else. And it is slowly, irreversibly converting that simple matter into more complex forms. This is not a process that can be reversed on any meaningful scale. The helium made in stars today will not become hydrogen again. The carbon in your body will not return to being the helium and hydrogen from which it was forged. The gold in a wedding ring or a museum artifact was created in a neutron-star merger or a supernova explosion, and it carries within its atomic structure the memory of that violent origin, that unrepeatable moment when it came into being. This is, perhaps, a comforting thought for a sleepless mind. The universe is not cycling endlessly through the same states, is not trapped in an eternal return, is not doomed to repeat itself. It is going somewhere, even if that somewhere is simply toward greater complexity and eventual heat death. Each moment in cosmic history is unique because the chemical composition of the cosmos is continuously changing, Because the stars are burning their bridges as they go. Because the past is genuinely different from the present. And the present will be genuinely different from the future. The hydrogen that burns tonight will never burn again. The supernova that explodes tomorrow will scatter elements that will drift through space for millions of years before perhaps becoming part of a new solar system. New planets, perhaps new life. And that life, whatever form it takes, will be built from atoms that carry within them the history of cosmic transformation, the record of a universe that refuses to repeat itself. So perhaps, as you settle deeper into rest, you might take a moment to consider the atoms of which you are composed, the oxygen you breathe, and the carbon that forms the backbone of your molecules, and the iron that carries oxygen through your blood. All of these were forged in stars, in processes that cannot be undone. And all of them represent way stations along the universe's long chemical journey from simplicity toward complexity. You are not separate from this process, you are part of it. A temporary arrangement of star stuff that will eventually return to the cosmic cycle, your atoms perhaps finding their way into new stars and new worlds in the distant future. But that future will not be the same as the past. And the present moment, this breath, this heartbeat, this gentle drift toward sleep, is occurring in a universe that is slightly different than it was a moment ago, and will never be exactly this way again. The memory the cosmos cannot erase. There is a kind of comfort, perhaps, in knowing that nothing is ever truly lost, that every moment you have ever lived, every breath you have drawn, every small and unremarkable afternoon you have already forgotten, has left its trace somewhere in the vast accounting of the universe, written into the fabric of things in ways so subtle and so permanent that even the cosmos itself cannot erase them. And this is what we will think about now, gently, as we consider the strange and reassuring persistence of information in a universe that seems, at first glance, to be always changing, always flowing forward, always leaving the past behind. In the early 1970s, a young physicist named Jacob Bekenstein was working at Princeton on a problem that seemed, at first, to be a technical matter concerning black holes. Those regions of space-time where gravity has become so intense that nothing, not even light, can escape once it has crossed the boundary we call the event horizon. And Bekenstein was troubled by a thermodynamic puzzle, because it seemed that if you dropped something into a black hole, all the information about that object, its structure, its history, the particular arrangement of its atoms, would simply vanish from the universe. And this troubled him because it seemed to violate something deep and fundamental about how physics works, namely that information, at some level, must be conserved. Between 1972 and 1973, Bekenstein proposed something remarkable, which was that black holes must have entropy, that they must be, in some sense, thermodynamic objects that carry information within them, encoded on their surfaces. And he showed that the entropy of a black hole, which is to say the amount of information it contains or conceals, is proportional to the area of its event horizon rather than its volume, which was a surprising and somewhat mysterious result that hinted at something profound about the relationship between information, gravity, and the geometry of space itself. A few years later, in 1976, Stephen Hawking published a paper that seemed to complicate matters considerably. because Hawking had been working on the quantum properties of black holes, and he had discovered something unexpected, which was that black holes are not entirely black after all, but rather emit a faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. And this radiation causes black holes to slowly evaporate over unimaginably long timescales, shrinking gradually until they disappear entirely. And the troubling implication of this discovery was that if a black hole could evaporate completely, then all the information about everything that had ever fallen into it would seem to be destroyed forever, truly and irretrievably lost, which would violate the principles of quantum mechanics that say information must be conserved. This became known as the black hole information paradox, and it occupied the minds of theoretical physicists for decades, because it seemed to pit two fundamental theories against each other: quantum mechanics, which insists that information cannot be destroyed, and general relativity, which describes how black holes form and evolve. And Hawking himself believed for many years that information really was destroyed when black holes evaporated, that the cosmos did indeed have a way of truly erasing things, of forgetting completely. And he defended this position with considerable vigor and characteristic certainty. Meanwhile, other physicists were not so sure, and among them were Leonard Susskind and Gerard 't Hooft, who began developing ideas in the 1990s that would become known as the holographic principle, which proposed that all the information contained within a volume of space could be described by information encoded on the boundary of that region, much as a hologram contains three-dimensional information on a two-dimensional surface. And this principle suggested that information falling into a black hole might not be destroyed, but rather encoded on the event horizon in a scrambled but retrievable form, spread across the surface like letters rearranged into an unreadable but still existing text. The holographic principle was strange and counterintuitive, suggesting that our three-dimensional experience of reality might be, in some deep sense, a projection of information stored on distant, two-dimensional surfaces, but it offered a way to resolve the paradox, a way to preserve the fundamental principle that information cannot truly vanish from the universe, only be transformed and redistributed and scrambled into forms that might be unrecognizable but are never entirely gone. In the year 2004, Stephen Hawking conceded, after years of debate and reflection and the accumulation of theoretical evidence, that he had been wrong, that information is not destroyed by black holes, after all, and he paid off a bet he had made with the American physicist John Preskill by presenting him with a baseball encyclopedia, which was Preskill's requested prize, chosen because an encyclopedia is, in its way, a repository of information, and this concession represented a significant moment in the history of physics, because it affirmed that even in the most extreme environments, the universe can create, even at the edge of a black hole where space-time itself is twisted into strange geometries. Information persists, transformed perhaps beyond recognition, but never truly erased. All of this might seem very abstract, very far removed from your experience as you lie here listening, breathing slowly, feeling the gentle weight of your own body against whatever surface supports you. But the principles at work in these exotic scenarios of black holes and holographic boundaries are, in fact, universal principles that apply to everything, to every interaction, to every moment, to the very breath you are taking right now as you listen to these words, long before physicists were puzzling over black holes. A researcher named Rolf Landauer was working at IBM in the early 1960s on the relationship between information and physics. And in 1961, Landauer published a principle that bears his name, which states that erasing one bit of information, the smallest possible unit of information, requires a minimum amount of energy to be dissipated as heat. And this principle, known as Landauer's principle, established something profound, which is that information is not merely an abstract concept, but a physical thing, intimately connected to energy and entropy and the fundamental workings of the material world. What Landauer showed was that you cannot erase information without paying a cost, without generating heat, without increasing the entropy of the universe, and this means that in a very real sense, the universe keeps track. The universe records. The universe remembers in its way, because every process that involves information leaves a physical trace, a tiny increment of heat, a small disturbance in the arrangement of particles, a permanent addition to the cosmic ledger that can never be subtracted. The physicist John Archibald Wheeler, who had been a mentor to many of the great physicists of the 20th century, proposed in 1989 a phrase that captured something of this deep connection between information and physical reality. And the phrase was, "it from bit," suggesting that the physical world, the it, emerges in some fundamental way from information, the bit, and that at the deepest level of reality, the universe might be better understood as a vast network of informational relationships rather than a collection of material objects moving through empty space. Wheeler's proposal was speculative and philosophical, but it pointed toward a view of the universe in which information is not merely a description of physical reality, but is, in some sense, the substance of physical reality. And in this view, every interaction, every event, every moment is an exchange and transformation of information that leaves its permanent mark on the structure of things. And now we might think about what this means for you. Lying here, breathing softly, perhaps noticing the gentle rise and fall of your chest, the small movements of air in and out of your lungs. And it may seem like such a small and ordinary thing, this breathing, so automatic that you rarely notice it, so gentle that it seems to leave no trace at all. But even this small act, this quiet breath, creates disturbances that, theoretically, propagate forever. When you breathe, you move air molecules, and those molecules bump into other molecules, creating tiny waves of compression and rarefaction that spread outward, and your body, having mass, creates subtle gravitational effects. And when you move, even slightly, those gravitational effects change, and these changes propagate outward at the speed of light as gravitational ripples, impossibly faint, far too weak to detect with any instrument we could ever build, but real nonetheless, spreading outward into the cosmos forever, carrying with them, in principle, information about this moment, about you, about the fact that you were here, breathing, existing, in this particular place, at this particular time. The universe, it seems, is a kind of cosmic ledger, an accounting system of infinite precision that records every interaction, every exchange of energy, every movement of matter. And while these records may become scrambled and distributed and diluted beyond any practical possibility of retrieval, they are never erased. They are never lost. They persist in the fabric of space-time itself, written into the arrangement of particles and the propagation of fields and the slow expansion of space that carries all information outward toward an infinite future. This is not a mystical claim, but a physical one, grounded in the conservation laws and thermodynamic principles that govern everything in the universe. And what it means is that every moment you have ever experienced, every conversation, every quiet afternoon, every night of sleep, every forgettable Tuesday, has left its trace, has written itself into the cosmic record. And while you cannot access these traces, while they are spread too thin and scrambled too thoroughly for any technology to recover, they exist, they persist, they are, in their way, permanent. There is something restful, perhaps, in this thought, in the idea that nothing is truly lost, that the universe keeps its own records, that every moment matters enough to be remembered by the cosmos, even if it is forgotten by you. And, as you lie here now, breathing slowly, you are adding to this record, writing new lines in the ledger, creating traces that will propagate outward forever. And this moment, this quiet moment of listening and breathing and being, is being preserved in ways that no one will ever read, but that are nonetheless real. The air moves with your breath, carrying warmth and moisture and the subtle chemical signature of your metabolism. And these molecules will mix and disperse and be breathed by others and incorporated into plants and dissolved into oceans. But the information about their arrangement, about the fact that they were once part of your breath at this precise moment, is encoded in the correlations and entanglements that ripple outward through the physical world. And the gravitational ripples, those impossibly faint waves in space-time itself, carry outward from your body at the speed of light, and in hundreds of thousands of years they will reach distant stars, and in millions of years they will reach distant galaxies, and in billions of years they will still be propagating through the expanding universe. And while no instrument could ever detect them, while they are so faint that they are effectively nothing, they are not actually nothing. They are real waves in real space-time, carrying real information about the fact that you were here, that you existed, that you breathed. Each moment writes itself permanently into space-time's fabric, and the universe that refuses to repeat is also the universe that refuses to forget. And as you rest here now, you can let this thought settle over you like a gentle weight, knowing that you matter to the cosmos in this small but real way, that your existence is recorded, that your moments are preserved, and that even when you sleep, even when you dream, even when you forget yourself entirely, the universe remembers, in its way, and nothing you have ever done or been or felt has been truly lost, only transformed, only distributed, only written into the cosmic ledger in a script too fine for anyone to read, but too permanent for anyone to erase. And so we come now to the theories themselves, the careful frameworks that physicists and cosmologists have constructed over many decades, each one attempting in its own quiet way to explain why the universe appears so fundamentally resistant to repetition, why the cosmos seems to be designed, if we may use that word loosely, not for eternal cycles of the same, but rather for an endless unfolding of the genuinely new. Let us begin with Sir Roger Penrose, the British mathematical physicist who was awarded the Nobel Prize in Physics in the year 2020 for his work demonstrating that black hole formation is a robust prediction of the general theory of relativity. But Penrose has contributed far more than this to our understanding of cosmic structure. And among his most intriguing proposals is something called the Weyl curvature hypothesis, which attempts to explain a rather puzzling asymmetry in the behavior of the universe at its beginning compared with its end. The Weyl curvature, you see, is a mathematical measure of a particular kind of gravitational distortion, the kind that produces tidal forces and gravitational waves, the kind that stretches and squeezes rather than simply expanding or contracting uniformly. What Penrose noticed, and what continues to intrigue physicists to this day, is that the Weyl curvature appears to have been extraordinarily small, vanishingly close to zero, at the moment of the Big Bang, while it grows ever larger as the universe evolves and as matter clumps together into stars and galaxies and eventually falls into black holes. This asymmetry, Penrose argues, is not accidental but rather fundamental to understanding why time flows in one direction, why the past is different from the future, and why the universe does not simply run backwards or repeat its earlier configurations. From this foundation, Penrose developed an even more ambitious framework called conformal cyclic cosmology, often abbreviated to CCC, which proposes that the universe does, in a sense, undergo cycles, but not the kind of cycles that would permit genuine repetition. In Penrose's vision, each eon of cosmic history ends not with a big crunch collapsing back upon itself, but rather with an infinite expansion in which all matter eventually decays. All particles lose their mass, and the distinction between very large and very small becomes mathematically meaningless. At this point, through a peculiar property of conformal geometry, the infinitely expanded end state of one eon becomes mathematically indistinguishable from the infinitely small beginning of the next, and a new Big Bang emerges from the ashes of the old. But here is the crucial point for our purposes, the detail that makes conformal cyclic cosmology a theory of non-repetition rather than eternal return. Each new eon, while emerging from the previous one, does not inherit its specific configuration. The information about where particular particles were, what patterns they formed, what moments were experienced by whatever beings might have existed, all of this is lost in the transition, erased not by violence, but by a kind of cosmic forgetting that occurs as the universe expands beyond all measure. And so, even if the cycles continue forever, even if eon follows eon without end, each beginning is genuinely new, washed clean of the particulars that came before, and no moment from any eon will ever be precisely replicated in any other. We turn now to Sean Carroll, the American theoretical physicist who has devoted much of his career to understanding the arrow of time and who articulated his ideas with particular clarity in his 2010 book, From Eternity to Here, a work that has guided many readers through the perplexing relationship between physics and temporal experience. Carroll's approach centers on what is sometimes called the past hypothesis, a deceptively simple statement with remarkably profound implications. The past hypothesis is essentially the observation elevated to the status of a fundamental assumption that the universe began in a state of extraordinarily low entropy, that the initial conditions of the cosmos were highly ordered and special in a way that the laws of physics alone do not explain. From this low entropy beginning, the second law of thermodynamics ensures that entropy will increase over time, that order will gradually give way to disorder, and that the universe will evolve always in the direction of greater randomness, greater equilibrium, greater uniformity of temperature and distribution. What Carroll emphasizes, and what matters so much for our gentle inquiry into non-repetition, is that this entropic arrow of time is not a superficial feature of our corner of the universe, but rather a deep structural property of cosmic evolution as a whole. Because entropy increases, because the universe moves always from ordered states toward disordered states, and because there are vastly more disordered states than ordered ones, the probability of the cosmos ever returning to its initial configuration, or to any configuration it has previously occupied, is not merely small, but preposterously, incomprehensibly negligible. Carroll's mathematics makes clear that the phase space of possible arrangements is so unimaginably vast, and the trajectory through that space so inexorably one-directional, that repetition is not forbidden by any absolute law, but is rendered so improbable as to be effectively impossible over any timescale we might consider. A rather different perspective comes from Julian Barbour, the British physicist whose 1999 book The End of Time proposed a radical reconceptualization of what time actually is, or perhaps more accurately, what time is not. Barbour's approach, sometimes called timeless physics or the theory of Platonia, suggests that what we perceive as the flow of time, the succession of moments from past through present into future, is in some fundamental sense an illusion, a byproduct of how conscious beings like ourselves experience a universe that is better described as a vast collection of static configurations. In Barbour's framework, each possible arrangement of all the particles in the universe exists in a kind of timeless mathematical space, and what we call history is simply a path through this space, a trajectory that connects certain configurations to certain others according to the laws of physics. But here too, and this is the point that concerns our theme of non-repetition, the space of possible configurations is so fantastically immense that even the most extended trajectory through it will never retrace its steps. To return to an earlier configuration would require what Barbour calls a point in Platonia that has already been visited, and the mathematics of his framework, like the mathematics of statistical mechanics before it, suggests that the probability of such a return diminishes not gradually but catastrophically as one considers increasingly complex systems. Let us consider now the ideas of Lee Smolin, the American theoretical physicist who has proposed a framework called cosmological natural selection, a theory that applies evolutionary thinking to the cosmos itself in a way that suggests universes reproduce, evolve, and diversify much as biological organisms do. In Smolin's hypothesis, first articulated in the 1990s and developed in his subsequent writings, whenever a black hole forms in our universe, it gives rise to a new universe on the other side. A baby cosmos that inherits the fundamental physical parameters of its parent, but with small random variations, mutations, if you will, in the values of constants like the strength of gravity or the mass of the electron. If this picture is correct, and it remains speculative but internally consistent, then the multiverse is not a static collection of all possibilities, but rather a branching, growing, evolving tree of cosmological lineages, each universe slightly different from its ancestors, each giving rise to offspring that are slightly different again. In such a framework, repetition is not merely unlikely, but structurally excluded, because the very mechanism of cosmic reproduction ensures divergence rather than convergence, novelty rather than recurrence. Even if two universes happened by extraordinary coincidence to start in similar configurations, their subsequent evolution and reproduction would carry them along different branches of the ever-expanding cosmological family tree. Speaking of the multiverse, we should mention the work of Andre Linde at Stanford and Alan Guth at MIT, the physicists who developed the theory of eternal inflation and who showed that the rapid expansion of the early universe, far from being a singular event that happened once and ended, may in fact be an ongoing process that continues to generate new pocket universes, even as you listen to these words. In the framework of eternal inflation, our observable universe is just one bubble in a vast foam of cosmological structures, each bubble nucleating from the inflationary background, each expanding to become a cosmos in its own right, and each separated from its neighbors by distances so immense that they will never come into contact. The implications of eternal inflation for repetition are subtle but ultimately reinforce the pattern we have been tracing. While some versions of the theory suggest that every possible configuration of matter and energy is realized somewhere in the infinite multiverse, the question of whether you will experience the same moment twice remains firmly negative. For even if a perfect copy of this instant exists in some unimaginably distant pocket universe, it is not you who experiences it, not in any sense that preserves continuity of identity, memory, or subjective history. The copies, if they exist, are as separate from you as strangers in a distant city, sharing your configuration but not your narrative, your pattern but not your path. We come now to an older prediction, one that has haunted physics since the 19th century, and that provides a kind of temporal horizon against which all these theories of non-repetition must eventually be measured. In 1852, William Thomson, who would later become Lord Kelvin, articulated what he called the universal tendency toward the dissipation of mechanical energy, a principle that would come to be known as heat death. In Thomson's vision, the second law of thermodynamics implied an ultimate fate for the cosmos, a state of maximum entropy in which all energy has been distributed uniformly, all temperatures have equilibrated, all differences that might drive change or motion or life have been smoothed away into perfect, timeless, unchanging equilibrium. The heat death, if it comes, represents the final guarantee of non-repetition, because in a state of maximum entropy, there is nothing left to change, nothing left to happen, and therefore nothing that could ever repeat. It is not a return to any beginning, but rather a cessation of the very processes that make moments distinct from one another. In a sense, it is not that the universe refuses to repeat in the heat death, but rather that the universe ceases to generate the kind of distinct configurations that would make repetition a meaningful concept at all. But not all physicists accept that the heat death must be utterly barren. And here we may mention the work of Freeman Dyson, the British-American physicist who, in a 1979 paper titled Time Without End, explored the possibilities for life and thought in a universe that continues to expand forever without collapsing back upon itself. Dyson showed, through careful calculations and imaginative extrapolation, that intelligent beings might continue to exist and to think in such a universe, not despite the approach of heat death, but by adapting to ever lower temperatures and ever longer timescales. In Dyson's vision, the beings of the far future would slow their metabolism, extend the intervals between their thoughts, and reduce their energy consumption in proportion to the declining temperatures available to them. They would experience not a finite amount of subjective time before the darkness took them, but rather a potentially infinite sequence of experiences, stretched across physical timescales of staggering duration, each thought separated from the next by intervals that would seem like billions of years to beings of our era, but that would feel no different to the thinkers themselves. And here, too, even in this strange eternal afterlife of slowed cognition and minimal energy, repetition remains absent, because even Dyson's beings, conserving every scrap of energy, minimizing every process, would still be embedded in a universe whose phase space is too vast to revisit, whose configurations drift always into previously unexplored territories. What we see across all these theories, from Penrose's conformal cycles to Carroll's entropic arrow, from Barber's timeless Platonia to Smolin's reproducing universes, from Lind and Guth's eternal inflation to Kelvin's heat death and Dyson's infinite adaptation, is a common theme that emerges not from any single assumption, but from the convergence of many independent lines of reasoning. The cosmos, it seems, is architected for perpetual novelty rather than eternal return. The mathematics of high-dimensional spaces, the thermodynamics of entropy increase, the geometry of expanding space-time, the logic of evolutionary branching, all of these point in the same direction, toward a universe in which each moment is genuinely new, never to be precisely repeated, never to be exactly revisited, always and forever the first and only time that this particular configuration of all that exists has been or will be. And there is something restful in this knowledge, something that settles over the mind like a soft blanket as sleep approaches. You do not need to worry about repeating your mistakes in some future cycle of the cosmos, because that cycle will not contain you. You do not need to fear the boredom of having already experienced everything that you will ever experience, because the mathematics of possibility ensures that novelty is inexhaustible. You are here, now, in this particular moment, and the theories of physics, for all their abstraction and complexity, agree that this moment belongs to you alone, unrepeatable and unrepeated, a gift that the universe has given exactly once and will never give again. And so we arrive here, in this quiet space, where the breath you are taking right now has never been taken before, and where the particular arrangement of everything that makes you who you are in this instant has assembled itself for the first and only time in all of cosmic history. This is not a dramatic proclamation, but simply a gentle observation, a soft fact to rest beside as you settle deeper into wherever you happen to be lying. And, as the night continues its slow turn around you. The Japanese tea masters of the 16th century understood something profound about the nature of moments, and they gave this understanding a name that has traveled across centuries to reach us here tonight. Sen no Rikyu, who elevated the tea ceremony into a meditation on presence and impermanence, spoke of ichigo, ichi, which translates roughly as one time, one meeting, or perhaps more poetically, as this moment exists only now. The phrase emerged from the recognition that each gathering of people around the tea, each particular afternoon light falling through the paper screens, each configuration of host and guest and steam rising from the cup, would never occur again in precisely this way. The tea master did not find this tragic, but rather found in it a reason for exquisite attention, a cause for treating each moment as the rare and unrepeatable treasure that it genuinely is. You might hold this thought loosely as you rest, not as a burden of mindfulness, but as a kind of permission to simply be present with whatever this moment happens to contain, knowing that it is, in its own quiet way, singular in the history of the universe. Marcus Aurelius, the Roman emperor who wrote his private philosophical journal while camped with his armies along the Danube frontier nearly 2,000 years ago, returned again and again to the theme of impermanence as a source, not of despair, but of clarity. In the 4th book of his Meditations, he observes that time is a river of passing events, and strong is its current, and that no sooner is a thing brought to sight than it is swept by and another takes its place, and this too will be swept away. He encourages himself, and by extension encourages us, to consider that all things are of the nature of the universal, that they arise and pass, that their coming and going is simply the way of things rather than a problem to be solved. There is something deeply restful in this acceptance, something that releases the grip of anxiety about holding on to what cannot be held. The emperor, writing by lamplight in a tent while the rain fell on military camps and the vast machinery of empire turned slowly around him, found peace in understanding that the river flows always onward, and that to float upon it is the most natural thing imaginable. Consider for a moment, as your body relaxes further into rest, that the observable universe contains roughly 2 trillion galaxies, a number so large that it escapes ordinary comprehension and instead becomes simply a kind of vastness, a sense of depth beyond depth. Within each of those 2 trillion galaxies burn hundreds of billions of stars, and each star represents its own particular fusion reaction, its own precise dance of hydrogen atoms collapsing under gravity and releasing light that will travel outward for millions or billions of years. No 2 of these stars are burning in exactly the same way. No, 2 are converting matter to energy in identical configurations, and the light from each of them carries a unique signature, a particular story written in wavelengths and intensity and the subtle variations of stellar chemistry. You exist in a universe where even the fires of creation are unrepeatable, where the fundamental processes that illuminate the cosmos operate always in singular instances, never quite the same twice. The cosmic microwave background radiation that permeates all of space, that faint glow remaining from the universe's earliest epoch when light first escaped, the primordial plasma, has been traveling for approximately 13.8 billion years to arrive at this moment. The photons that reach Earth tonight, that pass through the atmosphere and continue onward into the darkness beyond, have journeyed across nearly the entire age of the cosmos, and they will arrive exactly once. Tomorrow night, the radiation that reaches us will have traveled from a slightly different region of that ancient light, will carry a minutely different configuration of information about conditions in the early universe. And the photons that touched our world tonight will have passed onward into the void, never to return. In this way, even our cosmic surroundings are perpetually unique, the universe washing over us in an endless stream of singular moments. Each night sky different from every night sky that came before. In 1977, when the Voyager spacecraft began their long journeys outward from Earth toward the boundaries of our solar system and beyond, they carried with them a golden phonograph record containing sounds and images chosen to represent life on our planet. The Voyager Golden Record holds the cries of humpback whales and greetings in 55 human languages, the sound of rain and surf and wind, photographs of a nursing mother and a page of a book, and the geometric patterns of mathematical communication. What the record represents, among many things, is an attempt to preserve one specific moment in human history, to capture a particular arrangement of our civilization and our world as it existed in that year, and send it outward into the permanence of interstellar space. The spacecraft continue traveling now, more than 40 years later, and they carry with them a fossil of 1977, a moment frozen in gold-plated copper, while the Earth they departed has changed utterly. All the people who chose those sounds and images have grown older or passed away, and the civilization that built the craft has transformed in ways that no one could have predicted. The record drifts on, a testament to the fact that moments do pass, that the only way to preserve them is to accept that the preservation itself becomes a new thing, a message from what was to whatever might eventually receive it. Annie Dillard, in her contemplative work, Pilgrim at Tinker Creek, writes about time and presence with the careful attention of a naturalist observing the small dramas of creek and forest. She notes that we are most deeply asleep at the switch when we fancy we control any switches at all, and that the world flows past on its own way, regardless of our attempts to direct it. She describes moments of seeing, truly seeing, the muskrat or the frog or the light on water, as instances of being fully present to the particular and unrepeatable instant in which one finds oneself. Her attention to the natural world around her home in Virginia's Blue Ridge Mountains became a kind of meditation on the once and only nature of each moment. Each encounter, each small life glimpsed in its brief passage. There is nothing to do about this, she suggests, nothing to fix or improve, only the opportunity to notice, to be present, to witness the unrepeatable as it unfolds. As you rest now, your brain is engaged in patterns of electrochemical activity that have never occurred before in precisely this configuration. The specific neurons firing in this sequence, the particular distribution of neurotransmitters across the countless synapses of your mind, the way your memories and perceptions and half-formed thoughts are assembling themselves in this instant. All of this represents a state that the universe has never previously achieved and will never achieve again. Your consciousness, whatever it ultimately is, rides upon this singular wave of neural activity like foam upon the surface of a never-repeated sea. The thought you are having right now, even if it seems mundane or scattered or only half awake, is genuinely novel in cosmic terms. A flickering pattern of information that exists only in this particular arrangement of matter that constitutes your brain in this particular moment. The atoms that make up your body have been assembled by billions of years of cosmic and biological history into this temporary configuration, and they will eventually disperse again to become parts of other things, other processes, other transient patterns in the ongoing reorganization of matter that constitutes the universe's endless creativity. But for now, in this moment, they are you, arranged in this precise way. And this arrangement is as unique as a snowflake, as singular as a fingerprint, as unrepeatable as the exact position of every galaxy in the observable universe at this particular instant in cosmic time. The breath you are taking now draws air that has been cycled through countless other lungs, human and animal, across the long history of respiration on Earth. But the particular arrangement of molecules entering your body in this inhalation has never been gathered together in precisely this way before. The oxygen that will cross into your bloodstream and fuel the quiet work of your cells arrives in a configuration that exists only now. And when you exhale, those molecules will disperse into patterns that will never reassemble, joining the vast atmospheric mixing that has continued since Earth first developed its gaseous envelope billions of years ago. This is beautiful, not in an urgent or excited way, but in the quiet way that a single candle flame is beautiful, or the way that a pebble resting at the bottom of a clear stream is beautiful. The once and only nature of this moment does not demand anything from you, does not require that you appreciate it with any particular intensity or record it for posterity or extract meaning from it. It simply is what it is, a singular point in the infinite possibility space of the universe, occurring now and only now, carrying you gently forward into the next moment, which will also be unique, and the next, in an endless progression of unrepeatable instants that constitute the experience of being alive. Marcus Aurelius would remind us that this is simply the nature of things, that the river of time flows on regardless of our feelings about it, and that to accept this flow is to find a kind of peace that resistance can never provide. Sen no Rikyu would invite us to be present with the tea, with the steam, with the particular quality of the light, knowing that this gathering will never happen again. Annie Dillard would encourage us to see what is actually before us, to be awake at the switch even if we control nothing, to witness the muskrat as it slips into the water and disappears, unique in all of history, never to be witnessed in exactly that way again. And the Voyager spacecraft drift on, carrying their golden records into the interstellar medium, preserving a single moment from a world that has already changed utterly since they departed, while the cosmic microwave background continues to wash over the Earth, ancient light arriving for the first and only time, and 2 trillion galaxies turn slowly in their gravitational dances, each star burning its unique fire, each moment of cosmic time unrepeatable in all of eternity. You rest now in the middle of all this, one particular pattern in the universal pattern, breathing air that has never been breathed in quite this way, thinking thoughts that have never been thought in precisely this configuration, experiencing a moment that the universe has never experienced before. This is not something to achieve or to grasp, only something to notice, softly, as you settle into sleep, as your breath slows and your thoughts drift, and the night continues its quiet passage around you. The universe, in its endless creativity, its constant production of the new and unrepeatable, is experiencing something through you that it has never experienced before and will never experience again. And in this gentle truth, there is nothing to fear and nothing to mourn, only the quiet beauty of the singular, the once and only, the moment that exists now and carries you gently, peacefully, into whatever comes next.